Welcome back from break. Now we are going to move on to learn if we are given the chemical formula for an ionic compound, how do we write the name for that compound? You need to follow the following steps in order to complete the name for naming ionic compounds. First, you need to identify the cation and the anion in the chemical formula. Locally, when you are given the chemical formula for an ionic compound, the first element is the metal or the positively charged polyatomic ion in terms of ammonium. And then the next element or polyatomic ion is going to be the anion. So understand that we always write the chemical formula as we learned previously, cation followed by anion. Now, understand that when it comes to the cation, if they live in group 1A, 2A, 3A, they are zinc, cadmium, silver. You're just going to write the name of the element. So this is why I was mentioning in the first half of the class, make sure that the tables that I indicate and the information that I tell you, that you are familiar with it. You know how the rules work. Because if you're not familiarized with the table, if you're not familiarized with the information, when it comes to writing chemical formulas or naming compounds, it can become chaotic really quick, okay? So let's just keep track of everything we do. Continuing on, if we have a cation that lives in group B, if is tin, antimony, lead, bismuth, you're going to quote unquote break the chemical formula into ions. Then you're going to use for naming the name of the element followed by a Roman numeral, and in parentheses we're going to indicate the charge of our cation. Notice that rule number 3 only applies for the sequence of elements that I mentioned there. Rule number 4, the anions, when they are nonmetals, you're going to name them by replacing the ending of the name of the element by the suffix IDE. Locally, you don't even have to think about, okay, how do we do that? Because you can see here that we have a table of the anions that you guys need to know. The anions that come from elements, you guys are responsible for knowing. The one that comes from nitrogen, which is known as the nitride ion. The one that comes from phosphorus, which is known as the phosphide ion. The one that comes from oxygen, which is called oxide ion. The one from sulfur, which is sulfide ion. We have the one from fluorine, chlorine, bromine, and iodine, which they are known as fluoride, chloride, bromide, and iodide, respectively. So again, when it comes to your anion coming from the nonmetals, you can see in the following table, what are their names? On rule number 5, what if I have cations, like I said in rule number 1, when it comes from ammonium, or if your anion comes from polyatomic ions, then you just use the name of the polyatomic ion. Here, I only included the table that is in the reference list for exam, but as I mentioned in the beginning of today's class, you are responsible for knowing the textbook table, which I believe, let me just double check so I don't give you guys incorrect information. It is table 6.7. And you also need to know the table that is in the reference list for exam. Understand that these two tables has many of the same information. It's just that, for example, when it comes to table 6.7, you may have like the bicarbonates, bisulfates, bisulfite, and you may have like dihydrogen phosphate and all of those. But there's many of them that they are in common between the two tables. So you need to be familiar with all of that information, okay? So in order to do this, let's actually do some examples of if I'm given the chemical formula for an ionic compound, how do I come up with the name? So as you can see here, we have a list specifically of ionic compounds, okay? Let's go through at least a couple of these, but I will, go through the process of how to do these. So again, remember the rules I just mentioned before. This is why it's important that we need to familiarize ourselves with the rules for ionic compounds. So in the first one, we have NaBr, okay? If we have NaBr, excellent for putting it in the chat. Sodium lives in group 1A, so we can just put the name of the element. If we go back to our rule, that's going to be rule number 2. Bromine is a non-metal. That is rule number 4. So to name this, just like it was put in the chat, we don't even have to break this into ions. We're just going to write the name of the first element, sodium, and then the name of the anion for bromine, which is bromide. Understand that in the chapter quiz, in the lab, and in the exam, when it comes to this, this is going to be an entry answer. You guys are going to be typing these names, and you need to follow the format that is given in order for you guys to enter the name. In the format that I tell students that they need to utilize, I mentioned, make sure that when it comes to this, you do not capitalize any of the two names. You need to put a space in between all of the components. So after, if you have something that is a transition metal, understand that you need to write the name of the element, space, in parentheses, the Roman numeral, space, and then the second component. Make sure that you follow the rules, you get used to the rules. You will have different instances that you're going to practice, but solidify that by the exam. And spelling counts. If you spell it incorrectly, understand that it's going to not give you credit for your work. Let's look at letter B, K2S. We have a group 1A and a group 6A. Excellent. This is potassium sulfide. Letter C, Mg3N2. Mg3N2. Yeah, we're going to fix that spelling. Magnesium nitride. Excellent. Letter D, nickel lives in group in group B, specifically in group 8B. Okay, so because nickel lives in group B and is going to be one of those elements that are going to have variable charge, for this element, we need to say, okay, NiCl3. This chemical formula came from Ni plus 3 and Cl minus 1. For those students that are like, wait, Dr. Luz, how did you get that? All I did is that I took this number and I assigned it back to nickel. See that next to nickel, there's nothing, is because there is the value of 1. So I'm going to take this value of 1 and assign it to chlorine. Remember, I always give you cation followed by anion. That's why we know nickel is +3. And then Cl is -1. Okay? Excellent job in the chat. The name for this compound is going to be nickel in parentheses, Roman numeral 3. And this is chloride. Okay? Letter E. That's another transition metal. Chromium. So this is 2O3. So I know that this came from Cr plus and O is negative. Based on the chemical formula given, what is the charge on that chromium? Based on the chemical formula given, what is the charge of that chromium? Excellent job. 3. Based on this chemical formula, what is the charge of that oxygen? Great. -2. Okay. Remember, oxygen is always -2 because it lives in group 6A. Chromium +3. So I can go ahead and name this. This is chromium 3 oxide. So chromium 3, not 2. Let's move on to the next one. I have Ni in parentheses. I have NO3. We learned a few moments ago about polyatomic ions. So the 2 components of this ionic compound is going to be Ni, which is my cation, and NO3, which is my anion. I went ahead and put the charge. That's fine. But what is the charge of the nitrate in this chemical formula? Great. So the name of this is going to be nickel 2 nitrate. What will be the name for letter G? The ionic compound for letter G. Excellent. Iron 3 carbonate. Put a 1 in the chat if you need the markings to understand the ions. What about letter H? What's the name of that compound? Letter H. Excellent job. The ClO4 is incorrect, but the first part is correct. So this is, I agree with the titanium 4. What is ClO4? It's not chlorite. Exactly, it's perchlorate. Lastly, letter I. What is the name of the compound in letter I? PbC2O4. Excellent. We're going to work on that spelling. This is lead, Roman numeral 2, oxalate. At first, we have the chemical formula PbC2O4. If we break this into ions, you're going to see that this is Pb plus 1, C2O4 minus 1. But when we look at oxalate charge, it is not -1. Okay, so we need to somehow explain, wait, why is it that it is -1 here? Well, if we look at the charge of oxalate, it is always -2. So if my chemical formula doesn't show any subscripts, then that means that the charge on my lead needs to cancel the charge on my oxalate. So this is +2. This is a special case, but you always have to pay attention whenever you have a group B element. When you look at the anion, the charge of the anion has to be correct. We didn't have that problem in letter D, E, or F because chloride, we assigned a charge of -1, and that's correct because it lives in 7A. Oxygen has a charge of -2 because it lives in 6A, and that is correct. Nitrate, when we broke it into ions, it has a charge of -1. And that is correct because that's always the charge of nitrate. But in letter I, at first, our oxalate was assigned the wrong charge. So we have to erase the one that was assigned, place the one that is correct, and then decipher what is the charge of my cation to correctly assign the name for the compound. Any questions? Naming ionic compounds. Lead does not always have a charge of +2. Lead, tin, antimony, bismuth are going to have variable charge like the elements in group B. So that's why we had to break into ions those chemical formulas. Again, this is why I keep on stressing to you guys that when it comes to all of the trends that I have talked until now, make sure that you guys do the textbooks. You practice with the worksheet. We have lab 4 where you're going to practice. In addition to that, if you go to, let me illustrate in a moment. Let me show you guys other resources that I placed for you on Canvas. Oh, this is not working. Give me a moment, because I want to make sure that you guys solidify the concept of naming. So you have lab 4 where you're going to practice, like I said. You have the worksheet. And then if we go to the Canvas site for the course, let me illustrate where else you guys can get practice, because I placed resources for you guys. Give me a few moments. I want to make sure that you guys see the resources that I placed for you. So if you go to the Canvas site, and this is how yours should look like. You see how it says nomenclature practice, inorganic nomenclature practice? As you can see, this is a website that I found where you can practice either going from name to formula, formula to name. And you can, this has quizzes. So let's say that we go from formula to compound name. You can see examples here. And then if you click on it, you can select, based on multiple choice, COCl3. This is cobalt 3 chloride. When you click on it, it tells you, congratulations, you have selected the correct answer. So this is ways that you guys can practice. I want to make sure that you guys know all the resources you have, because when it comes to naming, that is one of the concepts that students sometimes just wait to get to know, but it's important that you guys solidify that for exam 2. There were some questions in the chat. Let me see if they were answered. The charge for the ion depends on the chemical formula. It doesn't depend specifically on the anion. So we are deriving those charges because of the chemical formula that was given. So for group B, and for, as you can see, tin, antimony, lead, bismuth, all of those, because they have variable charge, then depending on the chemical formula that is given to us, that's how we're going to name it. The anion is just helping to, solidify the whole thing, but it all depends, base it on the chemical formula. Transition metals always rely on the cation to determine. Yes, transition metals, the cation charge is what tells us the Roman numeral. Great. Awesome. Any other questions? Naming ionic compounds. Excellent. So let's now move on to understand how to name molecular compounds. Because I want you guys to understand that when it comes to naming molecular compounds, you are going to, given a chemical formula, you will find a name. So all the work that we have done so far, it's been derived from the periodic table, because remember that your group number is going to tell you specifically how something gets to be a cation or something gets to be an anion. In molecular or covalent compounds, we are sharing electrons. So remember, these compounds come from sharing electrons. So the way that we have those chemical formulas is not specifically derived from the periodic table, because we can have more than 2 atoms coming together to make these compounds. The way that we name them is also a little bit different, okay? As you can see, when it comes to the rules for molecular compounds, you're going to name the first nonmetal or metalloid, because remember that many metalloids are going to form covalent compounds, and we're going to do that by their name, okay? Then you're going to write the name of the second nonmetal, okay, by using the rules that we did before. Now, let me remind you that in a covalent compound or molecular compound, that second nonmetal is not an ion. We are just utilizing the rules for it. Remember, they're sharing electrons. So you're going to the second nonmetal, write the name based on the table that we did before for the nonmetals. If you don't remember which table that is this one. So the second name comes from this table. You have nitride, phosphide, iodide, sulfide, fluoride, chloride, bromide, iodide, okay? Now, one of the key features for molecular and covalent compounds is the use of prefix. And there's rules for which prefix you're going to use and who gets a prefix. As you can see here, it tells you there's a prefix for the first one and there's a prefix for the second one. Now, the first nonmetal, if it has only one atom, meaning it has a subscript of 1, then it doesn't get a prefix, okay? If it has 2 or more atoms, it will get a prefix. Okay? So again, the first element that you see there, the first nonmetal, if it has a subscript of 1, it doesn't get a prefix. But it has 2 or more, it will get a prefix. The second nonmetal always gets a prefix. So let me just write it here in the notes so you guys can have that. So this prefix is going to be always. This prefix only for subscripts of 2 or more. Okay? Now, there is a rule when the prefix ends in a letter and the element name starts with a letter. When that occurs, understand that we're going to omit the vowel, okay, that we have at the end of the prefix, okay? So, for example, let's say that we have CO as a compound, capital C, capital O. You see that the carbon has a subscript of 1, so it's not going to get a prefix. So when it comes to naming, we're just going to write carbon. Now, how many oxygens do we have? Let's put it in the chat. How many oxygens do we have in this chemical formula? Great job, only 1. So we are going to say, oh, I need to put the prefix mono. What is the word that we're going to utilize for naming that second nonmetal? What is the word that we're going to utilize for that second nonmetal? Oxide. Excellent. So we are now going to write monooxide. Rule 3B establishes that what we're going to do is not include this, and this becomes one word. So this is monoxide. Okay, so the correct name for this is going to be carbon monoxide. Okay. Now, when it comes to the reference list for exams, there are some common names for selected molecular compounds that you guys need to know for exam 2. They are included right here. So you need to know this for exam 2. You need to know what is the chemical formula and what's the name. So you need to know that NH3 is ammonia. It is not ammonium. Ammonium is a polyatomic ion, so don't confuse those two. They're cousins of each other. Actually, ammonium comes from ammonia, but please do not confuse them. pH3, that is phosphine. C2H4, that is ethylene. C2H2 is acetylene. NO is nitric oxide. N2H4, that's hydrazine. NH2OH, that's hydroxylamine. N2O, that is nitrous oxide. NH2O, from day one, we learn it, that is water. So let's first practice, if we're given a chemical formula, how we're going to derive the name. As you can see, this is problem 4 and problem 5 in our in-class worksheet. Okay, so in problem 4, you're given the chemical formula, we're going to write the name. And in problem 5, you can see some examples in which you are given the name, and then you're going to write the chemical formula. So I'm going to do at least the first 2, and then we're going to, go through the other examples. In the first one, SO. S, the name of that element is sulfur. SULFUR. Throughout the semesters, I've seen that because in speaking, we say sulfur. I don't know why people put an E instead of a U at the end of sulfur. Please do not do that because you will get it incorrect. Sulfur, you see the correct spelling of it, okay? So this is sulfur. Great job, you guys on the chat. This is sulfur monoxide. Again, one oxygen, mono. And then oxide is the second word. So we delete the first vowel. So the ending of mono, and then this is monoxide. Number 2, this is carbon dioxide. Remember, that deletion of the vowel is only if they are the same vowel, meaning O and O. We also do it for O and A, okay? So here we have I and O. We keep the I, we keep the O. So this is carbon dioxide. So let me just write that note because I don't want students to be dropping the vowels here. So that's only for O and O. So things that end in an O, and then the next word starts with an O. And then if your prefix ends with an A, and then your next word starts with an O. So that's the only time that it applies. Let's look at letter C. So I'm just going to do this one. This is disulfur hexafluoride. Remember, it's fluoride, not fluorine. We're going to use not the name of the element. We're going to end these in IDE. Put a 1 in the chat if you want to do a few more. Put a 2 in the chat if you got this, and you can move on. Excellent. People want more practice. Then let's go through these. So the next one, P2. What word do we use for showing that we have 2 of those P's in it? Great job. Diphosphorus. And then the 10 O's. What word do we use for representing the 10 O's? Decoxide. Because remember that in this case is deca plus oxide. For those of you that are not familiar with the prefixes, let me write it here. The prefixes are on table 6.12. So again, a subscript of 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 penta, all the way to deca. Okay, so that's where we go. That's where we got the prefixes from. Okay. Let's do a couple more. N2O4. What's going to be the name of that? N2O4. Great job. Dinitrogen. Tetroxide. Let's do one more. NCl3. What's the name of that? Great job. That is nitrogen. Trichloride. There are more examples of this in the in-class worksheet. Now, when it comes how to write the chemical formula for molecular compounds, okay, you have to make sure that, again, you look at this table to know at least the common names of things. If not, the name will tell you what subscript you're going to use. And please do not reduce the subscripts. The subscripts need to be present, representing how many atoms we have. So, what is the chemical formula of nitric oxide? That is a common name. Chemical formula for nitric oxide. Capital N, capital O. That's from the table that I just illustrated to you guys. So tetraphosphorus tribromide. So this refers to phosphorus and bromine. Tetra says that there's 4 phosphorus. Tri means that there's 3 bromines. Okay. What are the 2 elements in the next one? Dinitrogen trioxide. What are the 2 elements in the next one? Exactly, great. N and O. How many N's? Great job, you guys. And then 3 oxygens. Disulfur heptoxide. Disulfur heptoxide. What is the chemical formula of that? Excellent. I'm glad to see that a lot of students are getting this. Arsenic trichloride. Excellent. AsCl3. What about boron mononitride? Boron mononitride. Great job. Questions on how to go from knowing the components of an ionic compound and building the chemical formula for it, or if you're given the chemical formula for it, then building the name, or the same exercise, but for covalent compounds. Again, from name to chemical formula or chemical formula to name. Any questions? So there's a question of why NO is nitric oxide. That's the common name. And if we would do not the common name, it would be nitrogen monoxide. So again, this is just giving you guys the common names for them, just because you rarely see, like for example, ammonia. Ammonia technically is nitrogen trihydride. But in the textbook, it didn't give you guys the name when hydrogen is paired with other nonmetals. So that's why I didn't give you guys the hydride, because it's not in the textbook and there's no examples in there. Hydrazine is a compound that is in the textbook, and then usually they just give you the chemical formula, but hydrazine, for example, is dinitrogen tetrahydride. And then phosphine is phosphorus trihydride. But then again, for me, it's important that you guys know the common name, because for example, for my students that are going to be going into dentistry, NOx, nitrous oxide, is what that's laughing gas. Let me see, laughing gas, which sometimes is used as an anesthetic. That's nitrous. So that N2O, that's nitrous oxide. That is that gas sometimes it's put as an anesthetic. So I don't know, anybody has, because you know it happens. We're all afraid of the dentist. So hats off to you for the students that are going into dental hygiene. But some clients of yours may require nitrous oxide just for them to calm their nerves or whatever they need to get done. So understand that that nitrous oxide, that N2O, is just, you know, something good to know. Oh, there you go. Yes, for wisdom teeth. So nitrous oxide. Anyways, so that's just, you know, some compounds that I think it is important that you guys know the common names, but make sure that you practice. You guys will see in the chapter quiz when, because I have to make some modifications to the chapter quiz. I want to put a question that is similar to what you guys experience in the exam, so you guys get practice. Because this is the thing, I just went over all of the naming, and I find that when students are encountering names in general, then all the rules go out the window. So let me see. Oh, I think I have it here. This is how the in-class worksheet looks like. Ionic compounds, molecular compounds. This is where it's important that you guys know how to handle all of this, because you can see here that you have to write the name of the chemical formula for the following inorganic compounds. What does that mean? That here we have ionic compounds or covalent compounds. And I always find that when it comes to a question like part 6 in the in-class worksheet, then students don't even know how to handle it. Because they're like, wait, what, which one is ionic? Which one is covalent? What? So I'm like, take a moment, breathe, look at what is in front of you, and apply the rules similar to what we did, okay? So for example, to just mention this, if we look at problems 1 through 10, okay? We have some ionic and some covalent compounds, okay? So if I need to classify them based on the chemical formula that is in front of me, okay? There's only here 3 covalent compounds. There's only 3 covalent compounds. Let's put in the chat the numbers for the covalent compounds in numbers 1 through 10. There's only 3. What are the numbers that correspond to covalent compounds in numbers 1 through 10? Not 3, not 4, not 7. Excellent. 5 is a covalent compound. 9 is a covalent compound. Great. 5 is a covalent compound. So 5, we already mentioned that. There's 1 that is missing. So 5, I agree. 9, 10 is not a covalent compound. Thank you. Number 8. So the only ones that are covalent compounds is 5, 8, and 9. Everything else is an ionic compound. So it is important that you guys know how to decipher, okay, am I dealing with right now a covalent compound or an ionic? Because there's going to be, again, components. I need to make sure that you guys know how to do just ionic, just covalent, but if I give them to you combined, I also need to test that you know the difference between the two. So make sure that you guys practice problem 6 in the in-class worksheet.
So just as a reminder, covalent is metal and non-metals, and then ionic is a metal and a non-metal.
So when it comes to these, you're correct. Ionic compounds is metals, non-metals, but remember that ionic compounds can also be polyatomic ions and non-metals, or polyatomic ions, polyatomic ions. The main thing is my element going to form a positive charge and a negative charge? That's where the ionic comes from. Now, the covalent is just 2 or more non-metals. So as long as you know which ones are your non-metals in the periodic table, then you can tell, oh wait, any combo of 2 or more non-metals, those are my covalents. So it's easier to separate those first and then tackle the other ones and say, oh, okay, these are my ionics, because I have the first element is going to be from group 1A, 2A, 3A, or a polyatomic, or it's going to be from group B. So again, these are a lot of rules. So make sure, you guys, that this week you focus and you practice, because all of these concepts not only show up in chapter 6, they show up in chapter 7, they show up in chapter 9 and 10. We're going to do naming of inorganic compounds throughout. Any questions when it comes to naming? Excellent. So now that we know how to name inorganic compounds, I think the most fun that I have when it comes to naming inorganic compounds is looking at food labels or at products at home. Look at your toothpaste. There's a whole bunch of different inorganic compounds in there. Or like food products in general, you will see these inorganic compounds just being food additives and all that kind of stuff. So I am the type of person that looks at food labels and I'm like, oh, let me look at this compound. Oh, I don't feel comfortable with this element in my food. This one, okay, that's not that bad. So I love to look at food labels just to see, in terms of the ingredients, what kind of compounds are added to my foods. But now that we know about compounds, now we're going to focus on their structure. So when it comes to the structure, we are going to now go back and revisit the topic of electron dot formulas. Now we're going to call it by another name that is there, which is the Lewis dot formula. Lewis dot because of the scientist that created this concept, okay? So a electron dot formula or a Lewis dot formula is a diagram that shows the valence electrons in a molecule. Now, there are electron dot formulas that can be written for ionic compounds. And when it comes to ionic compounds, we see in those electron dot formulas where the cations, valence electrons, are going to be donated to the non-metal that is being paired with. So you can see here for the illustration of the compound calcium chloride, which is CaCl2, that we can see specifically how the 2 valence electrons in the calcium are going to the chlorine, but as you can see, each chlorine only needs 1 valence electron, and by using an arrow, we can illustrate where the electron comes from and where it's going. Now, you can see that as a result, that electron dot formula, this is going to be the final answer, where we see that calcium lost its 2 valence electrons, so that's why it has a charge of +2. And then the chlorines, each of them is going to have a -1 charge because each of them accepted 1 electron. So the correct electron dot formula for this ionic compound is, as you can see, that second illustration of the Ca+2 and each of the Cl minuses. Now, in the textbook, there's not a big discussion for the electron dot formulas for ionic compounds. The one that it is focused on is for the Lewis dot formulas for molecular compounds, meaning those covalent compounds that are going to be sharing electrons. In the following example, I'm illustrating how we have the following molecular or diatomic molecules. So this is a diatomic element. So when we see fluorine out there in the world, fluorine is always paired with another atom of fluorine. So what that means is that those 2 fluorines, each of them have 1 electron to share. And as you can see, The two electrons that are being shared, let me use my highlighter tool, are here. That is what is known as a bonding pair of electrons, because they are shared electrons between two nonmetals. Any electron that is not shared, that is known as a lone pair. And as you can see, each fluorine has 3 lone pairs. Think of lone pairs or pairs of electrons as shoes. Like when you buy a pair of shoes, you buy 2 shoes, okay? A pair of gloves, you buy 2 gloves, okay? So it's always 2, okay? Now, another way that we can illustrate that bonding pair is by drawing a line, okay? And this line is the same thing as a shared pair of electrons. It's just that that line, it's what is called a covalent bond. That's how we illustrate it. So I may understand how, if you have taken high school chemistry or AP chemistry, or you take chemistry 100, depending on the instructor and the school that you took it at, some people don't mind the first illustration where you are going to show your bonding pairs by the dots. In my class, we're going to graduate from that. Whenever there are shared electrons, I need you guys to understand that we're going to draw a line between the 2 atoms. So this illustration, again, that is on the left, I understand what it means, of course, but understand that in this class, I want to see shared electrons. Let me just highlight these again. I want to see those shared electrons between 2 atoms as a line, okay? Because those are the type of structures that I'll be showing you guys. So I need you to be familiar with that. Now, I want to make sure that you guys know that fluorine is not the only element that can be found as a diatomic molecule, okay? Hydrogen, nitrogen, oxygen, chlorine, bromine, and iodine are also elements in the periodic table where whenever we find them, is going to be as a diatomic molecule. This is something that you guys need to know for the exam, because when we do reactions in the next chapter, you guys need to know, okay, how in a reaction, if I say this reacts with fluorine, you need to know, oh, wait, fluorine, F2. Or this reacts with oxygen. Don't assume that is, oh, oxygen. I'm just going to write the letter O. No. In a reaction, we're always talking about diatomic molecules, especially if our reaction has any of these elements. So you need to know the list of diatomic elements for exam 2. Okay. Now, how do we develop the drawings of these electron dot formulas for covalent compounds? There are some rules, okay? And here I illustrate the rules that you guys need to be familiar with, okay? So these are the rules for drawing Lewis dot diagrams. I'm going to mention them first, and then we're going to practice. So as you can see here, when it comes to drawing Lewis dot diagrams, the first thing that we need to do is add up the valence electrons that each atom has in the molecule, okay? So when I look at the periodic table, where do I get this from? Where do I get this information? And don't say memory. You look at the periodic table, and the periodic table is going to tell you. Where do we get that information from? The number of valence electrons for the atom in a molecule.
The periods.
Not the periods.
Groups.
The groups. Excellent. Yeah, if it's not one, it's the other, right? So the group number. Okay, that's where I get that from. Now, as we're going to see in some of the examples that we have here in the in-class practice that we're going to do, sometimes we're going to have charged molecules. And particularly in the examples that we're dealing with, it's going to be our polyatomic ions, the ones that we're drawing, those charged species, right? Now, if your polyatomic ion has a negative charge, then you're going to add 1 electron per the number that is in the charge. So for example, if you have nitrate, when we're calculating the valence electrons for nitrate, because it's a negative one, we're going to add 1 electron. For example, if you have carbonate, which is CO3, 2 negative. So once you count the valence electrons that are going to be contributed by carbon, by oxygen, then you add 2 electrons because it is -2. Now, if you have a polyatomic ion, and we only have one, right? That has a positive charge, ammonium. Ammonium is NH4 positive. Because ammonium has that positive charge, understand that we're going to then subtract an electron from the valence count, okay? But again, we're going to practice a few moments so you guys see that. So that's rule number 1. Then you're going to write the symbol for the central atom, okay, in the middle. So how do we even determine what's the central atom? We mentioned before the whole idea of metallic character, okay? So when it comes to metallic character, typically what we have as the central atom is going to be the atom that is going to be the least metallic. But again, we're talking about nonmetals. So anybody that is a little bit more towards the left of the periodic table in terms of the periods, then we are going to have as a central atom. There's some exceptions to the rules, but I will outline them as we go through this. And then, as you can see, you're going to use a pair of electrons to form bonds between the central atoms and then remaining atoms. This is what I like to call the skeletal structure. And ideally, because there is a particular rule that we need to follow, which is called the Octet Rule, we need to make sure that we just bond the atoms to the central one, okay? But again, I'm just mentioning it in words. We're going to see it in practice in a few moments. Then you're going to count the number of electrons that are remaining, and then you're going to distribute it according to the Octet Rule, meaning that most atoms want 8 electrons. That varies because there are elements that we're going to see in a few moments that don't want 8 electrons, like hydrogen, like boron, like beryllium. But in general, many atoms, except those 3, are going to want 8 electrons, okay? And if there's not enough pairs of electrons, we have to make sure that the most electronegative elements are satisfied. We are going to learn about electronegativity in tomorrow's class. But again, I'm just going through this. And then we're going to start shifting the pairs of electrons into double bonds and triple bonds to satisfy the Octet Rule. And then if it happens to be that you have any other extra electrons, we're going to stick them on the central atom, okay? So again, all of these are words, words, words. I think that this is better illustrated when we practice. So when I just mentioned a few moments ago that they are going to be some atoms that don't want 8 electrons. In this class, I want you guys to know the rules for these 3 exceptions. For my students that may need to take other chemistry courses, I'm just gonna write it here for Chem 104. For my students that may have to take Chemistry 110, or your path in education takes you to advanced courses, understand that other nonmetals like phosphorus, sulfur, chlorine, bromine can form more electrons than 8, okay? But in this class, the exceptions that you guys need to know are the ones that I illustrated with the 3 red arrows. Hydrogen only wants 2 electrons, okay? So if you draw a line to hydrogen, you're done. Hydrogen doesn't want anything else. Hydrogen doesn't like lone pairs if it's sharing electrons already. So understand that hydrogen needs 2. Beryllium, which is the exception of group 2A, beryllium makes covalent compounds, not ionic. It only needs 4 electrons in order to form its noble gas configuration. Boron only wants 6 electrons. So when it comes to this rule for the octet rule, remember the exceptions for hydrogen, boron, and beryllium. They don't want 8 electrons around them. They want, based on the information that I just provided to you guys. Let's at least do a couple of examples to finalize this concept. And this is where we are going to start tomorrow also, okay? So as you can see here, we have 6 examples of molecules, okay? In the first step, when we're building the Lewis dot formula for a compound, is that we calculate the number of valence electrons available for bonding. I'm going to do it for letter A. If you're a student that is a little bit more advanced, please go ahead and do B, D, and E. But again, I'm going to explain everything for letter A. So looking at letter A, this is how I count my valence electrons available for bonding. Hydrogen lives in group 1A. That means that it has 1 valence electron. Now, there are 2 hydrogens in this chemical formula. So I'm going to take the number of valence electrons, multiply them by the subscript. So that means that into this chemical formula, hydrogen is contributing 2 valence electrons for bonding. Sulfur lives in group 6A. That means that it contributes 6 valence electrons to this chemical formula for bonding. There is only 1 sulfur here, so sulfur overall is contributing 6 valence electron. So when I'm trying to determine the total number of valence electrons available for bonding, I'm going to do 2 electrons plus 6 electrons. So that means that to build the Lewis dot formula for H2S, okay, I know that overall there's 2 from the hydrogen, 6 from the sulfur, so there are 8 electrons available for bonding, okay? Now, if I look at my metallic character rules, okay, understand that for metallic character, technically hydrogen is going to move where it is in the periodic table because it is a nonmetal, and is going to sit next to helium in the periodic table. So let me go to chapter 4 so I can show you how we visualize this in terms of the periodic table. So you see how hydrogen is all the way left? I don't want you to say, oh, hydrogen is more metallic. No, it's not, my friends. Hydrogen is going to be 4 metallic character on top of fluorine. So that means that sulfur, okay, is going to be the central atom, okay? For this. Let me go back. So sulfur is going to be our central atom. So sulfur is our central atom. Because we have to look at metallic character. Let me just verify this. Give me one moment. Hold on. Let me just write it here because I think that's going to be easier for you guys. So the central atom is going to be the atom with the lowest subscript. Least electron, electronegative. That's basically the trend. It's just that when it comes to the trends, I haven't mentioned to you guys the metallic, the electronegativity. You guys know metallic character. And then when it comes to metallic character, sulfur has more metallic character compared to hydrogen. So that's why sulfur is. Here you go. The central atom is going to have the lowest subscript, and it's going to be the least electronegative. Electronegativity we will talk about tomorrow. Remember that metallic character doesn't tell you if something is a metal or not. Metallic character is a property, okay? And if we go back to, sorry, I will show the notes in a few moments. Let me just go back here. The metallic character, it's illustrating that something is able to lose electrons easily. It doesn't tell you if something is a metal or not. There is a trend, right? The most metallic things are going to be towards the left of the periodic table. We're going to see an increase in metallic character as we're moving down within a group, or as we move from left to right in the periodic table. So Metallic character decreases as we move left to right, but then it increases as we move down. So in this case, hydrogen and sulfur are not in the same column, right? Because we're visualizing hydrogen next to helium, but sulfur is below, it's in period 3, okay? So technically it's more metallic in terms of the trend. So right now, because metallic character is the only thing that you guys know, again, in these nonmetals, the ones that have more metallic character are going to be our central atom. But when we go back to what we were talking about, and again, this is the note, electronegativity is something that we will mention in a few moments, or not today, because we don't have time for it today, but tomorrow in class. This whole statement of electronegativity is going to, again, will be repeated. So let me just at least introduce this first one. So sulfur is going to be my central atom. Then to that central atom, I'm going to attach all the atoms that I have, which are the hydrogens. Remember that in rule, when it comes to this, we're going to write the central atom, and then we're going to form bonds between the central atom and all the atoms that we have here, which are hydrogen. So it's kind of like everybody's touching the central atom. Okay, so hydrogen, each of the hydrogens is touching that. Now, I mentioned to you guys already that the lines represent 2 electrons. So we draw 2 lines. So out of the 8 electrons, we already used 4. So minus 4 electrons. So we have 4 electrons left. I subtracted those 2 electrons because these lines, they each represent 2 electrons. Okay. Hydrogen, if it has a line, it doesn't get any dots. So I have 4 electrons left. The only atom in my molecule that can hold 8 electrons is going to be sulfur. So I don't do lines to sulfur, I do dots to sulfur, because those are the remaining electrons in the system. So I use my 4 electrons left. I use all of my electrons for bonding. This is the Lewis structure for H2S. So tomorrow in class, we are going to proceed and do the other examples that we have here for Lewis dot structures. So make sure that you review Lewis dot structures, how to find the valence electrons, because that is what we are going to be doing tomorrow in class. So that's all for today.